Good morning students. Welcome to my YouTube channel. So in this video, I will be discussing on one of the standard symmetric encryption technique known as data encryption standards. So before watching this video, I recommend you first you watch my previous video, that is Feistel cipher technique, because we are using the same Feistel cipher concept in both DAS as well as AES in the upcoming videos. Okay? So let's start the data encryption standard concept. Okay, the DES is a symmetric key block cipher technique which was published in 1977 by NIST, known as National Institute of Standards and Technology. And this DES was previously widely used before 1977, but today, because of its insecurity, the DES is not much widely used. Okay, so this is the basic encryption and the decryption process in DES. So the DES will take the input of 64-bit plain text and it will produce the output 64-bit ciphertext. And it will take the help of 56-bit key. Normally, there will be a 64-bit key that is converted into 64-bit. The more information about this key expansion or compression will be seen in the upcoming videos. So similarly, what are all this 64-bit ciphertext what we got? We are sending in a reverse cipher to get back your plain text. That is known as decryption process. So now let us see in depth on how this encryption and decryption will happen. Okay. So this is the basic structure of DES. So as I already told you, the plain text length in case of DES is 64 bits, which is shown here. The key length will also be of 64 length or 64 bits, but however here I have shown 56 bits. So we are reducing 64 bit to 56, which we will see in the upcoming video. Okay, so the total number of rounds we are using in DES is 16 rounds. Okay, and in each round we are doing some operations that we will see shortly. And along with all these entities, we have initial permutation before the round starts and also the final permutation after the 16th round. So these are the 5 things we should understand for DES encryption. Is it clear? So again I am telling, we have 64-bit plain text as the input. Next we have initial permutation. Then we need to go for 16 rounds. Each round will have its own operation. And lastly we have final permutation. In each round we are taking a 48-bit key that is coming from 56-bit key that is coming from 64-bit key as the input. So how it is converted 64 to 56, 56 to 48, that we will see shortly. And lastly, after doing all these operations, you will get 64-bit ciphertext. So now let us start what happens in the initial permutation, what happens in round functions, and what happens in final permutation. Okay, first let us see what happens in initial permutation. So this is the overall diagram of DES. As I told you, we are getting an initial permutation where 64 bits we are taking, and this is the 64-bit key that we are taking, that is converted into 56. That 56-bit key is converted into 48, and that 48-bit key is doing some operation with the each round. Okay, 16 rounds we are doing with each key. So normally the 64-bit key has been converted into 48-bit 16 keys. In each round we are using one key. So how that is done, this part we will see shortly. You need not to worry much about this. Now let us concentrate only on this. Okay, what happens in initial permutation, what happens in round function, and what happens in final permutation. Okay, first let us see what happens in the initial permutation. So as I already told you, once again I am telling, please watch my previous video known as Feistel cipher technique before moving this video. Okay. So now let us see what happens in the initial permutation. So in the initial permutation, we are just changing the positions of the character. For example, the first position has been shifted to 40th position. The second position has been shifted to 8th position. So this is how it happens. This is the initial permutation table. So the first position came here. The element that is present in the first position will be moved to this position. The second element will be moved to here. And the 58th position character will come to the first position. So like that, all the elements will be shuffled. Why we are doing this? Just to confuse the hacker or the attacker. Okay. So this initial permutation table will be shared between sender and the receiver, or the user 1 and user 2 before we are entering into the rounds. Okay. Hope you understood what happens in the initial round or the initial permutation. Okay, we are just changing the 36 bits positions. Okay, so these are the 64 bits positions. These are the 64 bits. Each bit position we are just swapping to the respective position. So first position will come here, second position will come here, third character will go here, like that. Okay, hope you understood the first one. That is what the initial permutation. Next, we will see the 64 bits after swapping will enter into the round function. So what happens in round function? Let's see that. Okay. So this is what happening in the round function. So once the 64 bits are entered, so in the round functions what happens? First, I told on the Feistel cipher technique. The 64 bits data will be divided into two halves. 32-bit left side part and 32-bit right side part. In the right side part, what happens? We are sending it to function, round function. In the round function, the first step is we are sending it to expansion box. We call it as expansion permutation. So what happens here? This 32 bits will be expanded to 48 bits. How it happens? We will see. Those 48 bits are done XOR operation with the 48-bit key. Then you will get 48 bits output. Okay, that we call it as a state. Those 48 bits are again sent to substitution box. We call it as yes box. So those 48 bits have been reduced to 32 bits. Those 32 bits are done now. The permutation box again we are sending, where some positions will be changed, and finally we will get 32-bit output. Those 32 bits output are done XOR operation with the left side 32 bits part. Once we have done left side 32 bit and the output of this function 32 bits, we have to do the XOR operation where you will get the right side part, which is of 32 bit. The remaining 32 bits we are taking as it is from the left side part, sorry, right side part, and we are putting it to left side. This will become 32 bit. 32 plus 32, which is again 64 bits. That will go input for the next round, round 2. So the same process will be done in the round 2. Like that, we need to do how many rounds? 16 rounds. Okay. Now let us see what happens in this expansion box, in this substitution box, in this permutation box. Let's see that. Okay. So this is what the round function. That is what I have shown here. So here, in each round, what is happening? I am just showing this. So this is what happening in each round. The data is divided into two parts, left side part and the right side part. The right side part is entered into the round function operation, and we are getting the right side part, and the right side part as it is we are taking to the left side part. Now let us see what happens here. Okay, this part. Okay, now as I told you, from the right side part we are getting 32-bit input. That is sent into expansion box. In the expansion box, it is converted into 48 bits. Why? Because we are doing XOR operation with this output, which is having a key length of 48 bits, but we are having only 32 bit here. So those 32 bits now we are converting into 48 bits. Thereby, this 48 bits and this 48 bits can be done XOR operation. So in order to do that, we need to expand this 32 bits to 48 bits. How we are expanding? See here. So this is what expansion table. So this is what your 32-bit input which you are getting. Okay. We have 8 bits, means 4 columns. Each column is of 8 bits, 8 into 4, 32 bits. Now, how this is converted into 48 bits? See here. We are taking the first column, okay, and we are pushing it to last one more column we are adding. What we are doing? This 5, 9, 13, 17, 21, 25, 29, we are taking here as it is. Okay. And this one, what we have, that is one, we are changing it to last element. Similarly, this last column, what we have, 4, 18, 4, 8, 12, 16, 20, 24, 28, 32, we are changing it to first column we are adding. One more additional column. So what we are doing, 4, 8, 12, 16, 20, 24, 28, these 7 elements we are writing here. Okay, and this 32 last element we are writing at the first. So in this way, we are adding 2 extra columns or 2 extra bytes, 8 elements. So this is of 8 bits and this is of 8 bits, totally 16 bits we are adding extra. And already we have 32 bits. Totally we will get how much? 48 bits. Okay. So in this way, we are just expanding 32 bits to 48 bits. So once we got 48 bits, we are just doing the XOR operation with the first key, that is K1, in the round 1 function. Okay. Here you can see the 48 bit what we are getting is done XOR operation with the 48 bits from the key. So then output we will get what? 48 bits. Now these 48 bits are sent to the substitution box. We call it as S box, where those 48 bits will be reduced to 32 bits. Why? Because we are doing XOR operation at the finally with the 32 bits of left side part. Because of that, we need to reduce this 48 bits to 32 bits. So what happens in the substitution box? Let's see now. So this is what happening. The 48 bits are coming to substitutional boxes and we are reducing it into 32 bits. So how it is happening? Let's see now. See here, this is what substitutional boxes where there will be total 8 substitutional box 1, 2, 3, 4, 5, 6, 7, 8. And each substitutional box is taking the input of how many bits? 6 bits. Okay, 6 bits. 6 into 8, 48 bits. Means each box is taking 8 bits. Means the 48 bit input what we are getting is divided into 8 blocks. Each block is of 6 bits. 8 into 6, 48 bits. So now let us go to first box, that is substitution box 1. So each box will have its own substitution table. Okay, like S box 1, box 2, third box, fourth box, like that. 8 boxes will have its own substitutional table. So this is what 8 boxes substitutional table. Okay, that is S1, S2, S3, S4, S5, S6, S7, and S8. Using these substitutional boxes, we are reducing the 48 bits into 32 bits. How? Let's see one example. I will take this one as the example now. S1 box. So as I already told you, it is taking 8 bits as input and we are producing only, 6 bits as input and we are reducing it into 4 bits. The output is 4 bits. Yes? Like that, every box will take the 6 bits as input and it will produce 4 bits as output. Like that, totally 8 tables we have, 8 into 4, 32 bits. So in this way, the 48 bits will be converted into 32 bits. Now let us see one example, that is substitution box 1. So where it is taking 6 bits as input and we are producing 4 bits as output. Let's see here. So here, this is one of the example. The input to the S box 1 is 1000011, which is of how many bits? 6 bits. Okay. So what is the output? It will be of 4 bits. So how we are getting, see, please observe carefully. The 6 bits are what? 1, 0, 0, 0, 1, 1, which is nothing but here. The 6 bits 1, 0, 0, 0, 1, 1. These are the 6 bits. So what happens here? The first bit and the last bit, we are considering it as row. Okay. The remaining 4 bits are considered as column. Okay. In the substitution table. First bit and last bit is how much? Row is how much? 1, 1, which is nothing but in decimal 3. Okay. Now column we will see. What is the column? 0, 0, 0, 1. In decimal how it works? 1. So it means that we need to check now third row and first column. Please keep in mind third row means it starts from 0 index. 0, 1, 2, 3. Third row means fourth row it will become, and 1 means first column. 0, 1. Here you go to the now table. Third row and first column. See here. First one, so 0, 1, 2, 3, 4 into 16 matrix. 0, 1, 2, 3, like that it will be till 16. So now what is the row and column here? What is the row? 3. What is the column? 1. Now let us see. Where is 3 here? Here. Where is column 1? Here. Now where it is intersecting? 12. That 12 is the output here. Represent this 12 in 4 bits. What is the value of 12 in 4 bits? 8, 9, 10, 11, 12. So 1, 1, 0, 0. So in this way, the 6 bits are converted into 4 bits. Like that, each box will convert 6 bits to 4 bits. Like that, totally we have 8 boxes, 8 into 4, 32 bits you will get as the output. This is how the substitution box will convert or will reduce 48 bits to 38 bits. One thing you should keep in mind here, as I told now, this is very important, the row and column. The first bit and the last bit are considered as row. Remaining 4 bits are considered as column. Clear? Okay. So in this way, now the 48 bits are converted into 32 bits. These 32 bits are again sent to one straight P box we call it as. So changing the positions again. That is also we have standard table. This is the straight P box, permutation box, where we have 32 bits. Okay. There are totally 8 columns, each of 4 bits, 4 bits, 8 into 4, 32 bits. Okay. So here we are changing the positions. First element will come to second position, in this position, and second will go here. Where is second? 2. Where is 2? It comes here. The third element will go here, and the 16th element will come first. Like that, all 32 bits will change its positions. Okay. So this is what stripe P permutation. So after doing this, we will get a 16 bits of output. Clear? So finally, you will get a 32-bit output. That is what we have shown here. Is it clear now? What happened? This 32 bits are sent to expansion box where we have converted into 48 bits. Then we have done 48-bit XOR operation where we got 48 bits as the output. Then we have sent to substitution box. Then we have reduced it to 32 bits. Then we have sent it to straight P box where it is got 32-bit output. And this 32-bit output are done XOR operation with the left side 32-bit. Okay, where you will get the output as right side 32 bits. And this right side part is sent as it is as the left side part of 32 bits. And this will become the input for round 2. 32-bit left side part, 32-bit right side part. And the same operations will be performed in the round 2. Like that, how many rounds we need to do? 16 rounds. So the output of the 16th round will be the cipher text. So now here the question is how this, I hope you understood now. So this is what we have done. Okay. We have done initial permutation, we have done. We went to each round, what is happening inside each round, and all the things will happen in the each round till 16 rounds. But here the problem is the 64-bit key, how it is converted into 48 bits. So I will tell in a simple way. So the more information you can watch my previous video. Okay, how the key expansion will be done in DS algorithm. So however, I will try to tell in 2 minutes how that is converted. So this is what the key expansion and also compression. So what we have, the input is 64 bits key length. That is what we have seen here. Yes or no? This is what 64-bit key. Okay. That 64-bit key is coming to the parity drop, we call it as, where 64 bits are reduced to 56 bits. How? We are just dropping few bits. Which bits? Parity drop, we call it as. So the 8th bit, 16th bit, 24th bit, 32 bit, 34th, 32nd position, 40th position, 48th position, 56th position, and 64th position. All those bits are dropped. Total how many? 8 bits. So out of 64 bits, 8 bits are dropped. These positions are dropped. So the remaining bits are 56. These 56, now what we are doing, we are divided into 2 blocks. One is 28 block, the other one is 28 block, which is 56. Okay, these are sent to what we call it as compression boxes. So in the compression box, what it will do, this will reduce into 48 bits. That is what sent to round 1. That is what we have seen here. Yes or no? See, 48 bits are came here. Okay, but now the question is how these 28 bits are converted to 48 bits. Okay, here is the compression box. You can see here. So this is the compression box. These are the 28 bits and these are the 28 bits. Okay. In this 28 bits, 9th position, 18th position, 22nd position, and 25th position elements are dropped. The remaining how many it will be? 28 minus 4, 24. Remaining 28 second block, 35th position, 38th position, 43rd position, 54th position elements are dropped. Remaining is how many? 24. 24 plus 24 how much? 48. So these are the 48 bits key we are generating from 56 bits. Okay. Hope you understood. So this is how we are getting 48 bits. Okay. So that 48 bit key we are sending it to each round. That is what I have shown here. Okay. Okay. But here the question is, you ask us doubt, sir. Then how you are getting 16 round keys? Here we are generating only one key. Then how we are getting 16 different types of keys, sub keys? So what happens here? So here is the condition. First round, second round, ninth round, 16th round. Sorry. Okay. First round, second round, ninth round, 16th round. We need to do one bit shift. So one bit position we need to change. For example, we have like one. This is what your key. This is what your 48-bit key in round 1. Okay. So first round, ninth round, 16th round, and second round, you need to do one position shift. Means 14th will go to 17th, 17th will go to 11th. Like that, one position will be changed. Then it generates another key. Like that, 4 keys will be generated in 1, 4, 9, and 16 with one shift. Okay? That is what the condition. 1, 2, 9, 16, only you should do one shift. Thereby, 4 keys are generated. Remaining all rounds, we need to do 2 shifts. Thereby, the remaining 12 round keys are generated. So 12 plus 4, 16 round keys will be generated. So in this way, 16 keys will be generated with the help of these shifting. So hope so understood. So in this way, the DES algorithm will work. So hope so understood now. Finally, I will take a 1 minute revision overall what I have did. So this is what we have seen. First, we have taken the 64-bit input and then 64-bit key. In the 64-bit plain text, we have sent to initial permutation. We have just changed the position. Then we have entered into the round 1. In the round 1, first what we have seen, 64 bits are converted into two blocks, left side 32-bit and right side 32-bit. And right side for 32-bit, we are sent to expansion box where the 32-bit are converted to 48-bit, and those 48 bits are sent to substitution boxes that are reduced to 48-bit keys is again done XOR operation with the 48-bit key where we got 48 bits output. Then those 48 bits are sent to what you call substitution boxes that are reduced to 32-bit. Then we have sent to P permutation where we got output as 32 bits. Then those 32 bits are done XOR operation with the left side part data. Then we got right side part 32 bits, and the right side part of 32 bits are taken as it is as the left side part. So in this way, those are sent to input for the next round. So this is what happened. And this key also we have seen 64 bits are reduced to 56 bits by removing the parity bits, and then those 64 bits are divided into 28 28, and then we have removed 4 bits in each block. Then we got 48 bits, and those 48 bits are used in each round. So lastly, we need to note one more point. So initial permutation we have done. So once 16 rounds are completed, we need to do what is known as final permutation. So this is what we have to do at the end. So this is what the table for final permutation. This one, the final. So the 64 bits what we are getting after 16 rounds. Again, we need to change the positions. So the first position will come here just to make the hacker confusion. Okay, and second position will come here, third position, fourth position, fifth position. Like that, all positions will be changed, and this will become the input for the next round. Sorry, after 16th round, this will become your final ciphertext. Okay, so in this way, the 64 bits plain text has been converted into 64 bits ciphertext. That is what I have shown in the starting diagram. 64-bit plain text are converted into 64-bit ciphertext with the help of DS cipher. So in this way, the DS algorithm will work. But in today's technology, because of this insecurity, we are not using this much. We are going for advanced encryption standard, which will be explained in the upcoming video. So in order to provide much security for this DES, we have what is known as multiple DES. Means instead of doing the encryption once, we can do twice. This is how. Since 64 bits plain text has went to DES cipher with key 1. What are the output we are getting? Again, we are doing encryption with key 2. So 2 times we are doing the encryption. Similarly, we are using the keys 2 times to decrypt. But the only condition is first time we need to use the key 2 at the decryption side, and next time we should use the key 1. Reverse case. So this is what happening. And if you want still stronger, then you can go for triple DS. 3 times you need to do the process. First time you should do the encryption with key 1. What are the output you are getting? You need to decrypt with the key 2. And what the output you are getting, again you need to encrypt with the key 3. Then finally what you will get is the ciphertext. But here we need to be very careful, because once you decrypt now, you are getting some data where there is a more chances of meet in the middle attack. So chances are more. So we need to be very careful there. Yeah? So whenever you are decrypting back using what we call that triple DS, reverse process is applied. First round, first time whenever decrypting, you need to use the key third key, and the second time whenever you are encrypting, you need to use the key 2, and third time again when you are decrypting, you need to use the key 1 to get back your plain text. So in this way, the triple DS will work. So hope so you enjoyed the video, and as per normal case, we will see the assignment to be done. Please post the assignment in the chat box. So the solution for this will be seen in the next video. Okay. So the assignments are: explain the role of the Feistel structure in DES. Okay. Why is the DES considered insecure in modern cryptography? Compare DES with AES, that is the Advanced Encryption Standard, in terms of security and performance. Write a simple Python programming to implement a DES encryption decryption using a same existing library. Okay. Hope you enjoyed the video. Thanks for watching and subscribe my YouTube channel for more videos. Bye.